Imagine you're sitting in a classroom, right?
Okay.
And it is exactly 10:37 a.m. You're taking this notoriously difficult history exam,
Oh, I hate those.
right? So you're sweating, you're struggling to remember exact dates, all these geopolitical shifts. But then you notice something incredible. The teacher has accidentally left a copy of tomorrow's newspaper on the very edge of your desk.
Oh, wow. Okay.
Yeah, and all the answers to the historical events you're being tested on, well, they're somehow printed right there in the future news.
That's convenient.
Very convenient. So if you use that newspaper to ace the exam, I mean, you aren't a genius historian. You have zero actual knowledge of history. You are just a time traveler cheating on a test.
Exactly. You're just copying the answer key. And, while that sounds completely absurd in a classroom setting, in the world of algorithmic trading, quantitative finance, computer models accidentally do this exact thing all the time.
Wait, really? All the time?
All the time. They secretly peek at that newspaper from the future. And when they do that, they generate the illusion of a wildly successful trading strategy.
Right.
They produce returns that make it look like you've, unlocked the secrets of the universe, when in reality, you've just written a bug that violates the linear flow of time.
That is just wild to think about. And that brings us to the core mission today for you listening. We are unpacking an intensely technical, but honestly, utterly fascinating source article today. It's titled Proving No Look Ahead in Multi-Timeframe Backtests by an author named Sunat.
Yeah, it's a fantastic piece of work.
It really is. And this exploration, it goes so far beyond just day trading or finance. This is really a profound look into how we validate complex systems.
Right.
We're going to explore how data can literally lie to us by leaking the future, and how a developer actually figured out a way to mathematically, undeniably prove that a complex software system is firmly rooted in the present moment.
Yeah, and what's fascinating here is that while standard trading models, they actually have straightforward ways to check for this kind of time-traveling bug.
If it's a simple model.
Right, exactly. Provided the algorithm is only looking at a single time frame. Like, if your trading bot only looks at 1-minute candles, tracking down a leak from the future is manageable.
Okay, that makes sense.
But things get incredibly dangerous and mathematically really murky when multiple time frames start interacting with each other.
The multi-timeframe minefield.
Right. So today we're breaking down how this developer found a hidden temporal leak in a multi-time frame system, how they engineered a flawless memory buffer to prevent it, and then, and this is the crazy part, how they subjected their own architecture to 25 relentless checks just to prove, beyond a shadow of a doubt, that their code couldn't see the future. We're looking at this specific, totally ruthless validation framework called the Shifted Future Probe.
I love that name. Shifted Future Probe. So, to really grasp the brilliance of this solution, we first have to understand the specific trap that catches so many algorithms off guard.
Yeah, we have to lay out the problem.
Exactly. How do multiple clocks running at entirely different speeds create an invisible trap? The source text sets up a very specific scenario, a triple time frame momentum rule. So let's break down exactly what that entails.
Okay, so whenever you're analyzing financial markets, you have to decide on the resolution of your data, right?
Right, like how zoomed in you are.
Precisely. Are you looking at price changes? Every second, every minute, every day. The source details a strategy where the base clock, the fastest one, the foundational heartbeat where all the actual buy and sell decisions are executed, is ticking every 1 minute.
Okay, so 1-minute bars.
Right, 1-minute candles. But the strategy doesn't just blindly follow that fast clock. It also consults two significantly slower clocks, a 1-hour trend and a 15-minute trend.
And that makes a lot of sense because if you only trade on the 1-minute chart, I mean, you're going to get chopped to pieces by market noise, right?
Oh, absolutely.
A single large order from a bank or an institution can cause this massive 1-minute spike that just immediately reverses. So by looking at the 1-hour and 15-minute clocks, you're essentially setting up a filtration system.
Exactly. The slower trends act as
gates. Okay.
Right. They either allow a trade to pass through or they deny it entirely based on the broader macroeconomic current. The 1-hour and 15-minute gates say, hey, the overall ocean current is moving north, or the current is moving south.
Got it.
Meanwhile, the fast 1-minute clock acts as the trigger. Specifically, the strategy looks for a 1-minute indicator in this case, a whole moving average crossed to fire.
Okay, let's pause on the whole moving average, or HMA, for a second, because the choice of indicator here actually highlights why timing is so critical.
Yes, it's a very intentional choice.
Because the standard moving average, like, say, a simple moving average, it has a lot of lag.
Too much lag for this kind of strategy.
Right. If a stock suddenly drops, a 50-period simple moving average takes a long time to reflect that drop because it's just weighing the past 50 minutes equally.
Exactly.
But the HMA was specifically designed to almost entirely eliminate that lag. It uses this complex calculation involving weighted moving averages of half the period and the full period, basically to hug the price action incredibly tightly.
That is a crucial detail. The algorithm is using a hyper-reactive indicator on a 1-minute time frame, specifically because it wants to catch momentum shifts the absolute second they happen.
Right.
But it only acts on that hyper-reactive trigger if the slower, more deliberate 1 hour and 15-minute gates agree with the direction.
And what about getting out of the trade?
Well, exits happen when those higher time frame trends reverse against the position,
Hmm?
or when the fast, lower time frame HMA crosses back in the opposite direction.
Which means the computational load, the sheer amount of checking this algorithm has to do, is immense.
Oh, it's massive.
I mean, if my base clock is ticking every single minute, I have to check the 1-hour gate, check the 15-minute gate, and check the 1-minute trigger, and I have to do that 60 times every single hour.
Yeah, the source actually breaks down the exact math on this.
Sure.
Between checking the 3 distinct time frames, evaluating the entry trends, the exit conditions, and checking these directional separation gates to ensure the trends aren't just, flatlining.
Yeah.
The algorithm is performing roughly 180 distinct per bar reads per hour.
Wow. 180.
Yeah, 180 times an hour, the code essentially screams, what is the exact state of the market right now across all time horizons?
Okay.
And every single one of those answers must only use information that a live trading bot sitting on a server somewhere would actually have access to at that exact microscopic instant in time.
And this brings us right back to my 10.37 a.m. history test analogy, because this is where the multi-time frame minefield detonates. The trap here is what the author defines as the forming bar problem.
Ah, yes, the forming bar problem. It is the silent killer of historical backtests. It ruins careers, honestly, and blows up trading accounts.
Let's walk through the mechanics of it.
Okay, imagine your backtest is running, and the simulated clock hits exactly 10.37 a.m.
All right, I'm at 10.37.
The algorithm is deciding whether to buy or sell based on the 1-minute bar that just closed. The strategy rules clearly state it must consult the 1-hour trend gate to see if the broader market is favorable.
Right, it needs to check the ocean current.
Exactly. So the code asks for the status of the 1-hour candle that covers the period from 10:0000 a.m. to 11:00.
Okay, but there is a massive fundamental paradox here. What is the actual status of that 10.000000 a.m. candle at 10.37?
Well, it doesn't exist yet. I mean, it exists partially, but it is not finished. It's still forming.
Okay.
The final closing price that hour, the permanent data point that will go down in history, that will materialize until 10.59 and 59 seconds.
Yes. In the real world, in live trading, all you can possibly know at 10:37 a.m. is the running close.
The running close. Right. The running close is simply the current price of the asset at the close of the 10.37 1-minute bar. That is all the information that is mathematically manifested in the universe at that exact moment.
Because 10.38 hasn't happened yet.
Exactly. But when developers test their strategies using historical data, they often use standard libraries, like pandas and Python, to speed things up. And this introduces the naive multi-timeframe backtest bug.
Okay, let's unpack this. How does standard data analysis software accidentally create a time machine?
It happens because data analysis tools are designed for efficiency, not necessarily for temporal causality. They make it incredibly easy to take your fast 1-minute data and resample it.
Resample it. Okay, what does that mean practically?
You tell the software, hey, take all these millions of 1-minute rows and group them into 1-hour blocks. The software efficiently calculates the open, high, low, and close for every hour and builds this beautiful clean table of 1-hour closes up front.
So it pre-calculates everything.
Right, and then it often forward fills that data so it can align with your 1-minute timeline.
Oh, I see. So it takes the final result of the 10.00 to 11.0 a.m. hour and effectively pastes that final closing price onto every single minute from 10.01 to 11.0.
Precisely. So when your backtesting algorithm is simulating the trading day, stepping forward minute by minute, and it hits 10:37 a.m., it asks the dataset, hey, what is the 1-hour close for this period so I can evaluate my gate?
And the dataset gives it the 11:00 a.m. answer.
Yes. The resample dataset happily hands it the final 10:00 to 11:00 a.m. close.
Okay. I want to play devil's advocate here because we really need to understand the magnitude of this error. I'm looking at this mathematically and thinking, is this actually that catastrophic?
Oh, it is.
But hear me out. We are talking about a very small window of time. At 10.37, you're just accidentally getting the price data from 11.00. It's only a 23-minute difference. In the grand chaotic scheme of the crypto market or the stock market, is a 23-minute sneak peek actually going to invalidate an entire quantitative strategy?
It is absolutely, unequivocally devastating. You have to think deeply about what this specific strategy is trying to do. It's a momentum strategy. It is actively looking for sudden surges in price. The higher time frame close, that 1 hour final closing price, is the aggregate result of the next 23 minutes of price action.
Right.
It is the strongest possible predictor of the near future 1-minute returns you are about to trade. If you know exactly how the hour is going to end at 10:37 a.m., you know exactly whether the momentum is going to sustain or collapse over the next 23 minutes.
Oh, wow. Yeah, you know the answers to the test before you've even taken it.
Exactly. You are leaking a full 59 minutes of future data into your present decision at 10.01, 58 minutes at 10.02, and so on. It is quite literally reading the answer key.
Now, the source mentions that in a previous article, they dealt with something called an execution leak, which they fixed with a 1-bar shift test. And we need to draw a hard line here because an execution leak sounds similar, but it is mechanically very different from what we are dealing with today, isn't it?
Entirely different. Yeah, an execution leak is a mechanical routing error. It happens when your algorithm decides entirely legitimately to buy right now at 10.37, but the simulation accidentally records the fill price from 10.38.
So you just got the price from 1 minute too late.
Right, you peaked 1 minute ahead for your execution price. The fix for that is simple. You just instruct the simulation to shift the execution fill forward by 1 bar so it aligns properly.
Okay.
But what we are talking about today is an indicator leak. The indicator itself is structurally contaminated. Shifting the fill of your trade by 1 minute doesn't fix anything because the core mathematical logic that decided whether to trade at all was fundamentally poisoned by future knowledge. The leak lives in the DNA of how the indicator is calculated.
That is terrifying for a developer. So having mapped out this absolute minefield of the naive backtest, we need a mechanism to safely navigate it. We need a way to build a clock inside the computer's memory that physically cannot access data from the future.
Right. And the solution lies in abandoning that naive resampling approach entirely and instead mimicking the architecture of the actual live trading bot with obsessive precision.
Mimicking the live bot.
Yeah.
Okay.
The source material outlines a specific class built in their code base called running candle buffer. This simulator enforces what they call closed bar semantics.
Closed bar semantics. Let's unpack that. I think we need a physical analogy for this because visualizing how a computer manages arrays of memory can get abstract very quickly for you listening. Let's compare closed bar semantics to a massive sports scoreboard in a stadium.
I like that. How does the scoreboard analogy work here?
Imagine the scoreboard tracks points quarter by quarter. When the first quarter ends, the final score for that quarter is painted onto the board in permanent paint. It is locked. It will never change.
Paint.
But the second quarter score isn't painted. It's on a digital ticker. Every time someone scores, that digital ticker updates instantly. The numbers keep spinning and changing dynamically until the buzzer sounds to end the second quarter. Only when the buzzer sounds does the digital ticker freeze, and the groundskeeper comes out and paints that final number permanently onto the board.
That is a phenomenal way to visualize a memory buffer under closed bar semantics. Yeah. The code is streaming the fast 1-minute base bars into fixed period candles, just like putting points into quarters on the scoreboard.
Exactly.
The unbreakable rule of closed bar semantics is this. When the algorithm calculates its historical indicators, the moving averages that require past data, it is only ever allowed to look at the permanent paint. It can only pull final closes from candles that have officially ended.
So let's bring it back to our 10.37 a.m. trading decision. If I am the algorithm and I call up the running candle buffer to ask for the 1-hour trend, what exactly does the scoreboard show me?
Well, under strict closed bar semantics, when you ask for the 1-hour trend array at 10:37 a.m., the buffer hands you an array of data. It gives you the permanent paint of the 8.0 to 9.0 hour because that's finished. It gives you the permanent paint of the 9.00 to 10.00 hour because that is finished. But for the current, active hour, the forming candle contributes exactly one single number to the array.
And that's the running close?
Yes, the running close. The close of the 10.37 minute. That is the digital ticker. That is all you get.
And then when 10.38 prints...
When 10.38 prints, That single active slot in the array simply updates to the 10.38 close. The candle remains unsealed. The digital ticker spins.
So it just replaces the 10.37 number with the 10.38 number.
Exactly. Only when the clock strikes exactly 11:00 does the 10.59 close become the newly closed candle's final permanent value. The groundskeeper paints it. And instantly, a fresh forming slot opens up for the new 11:00 to 12:00 hour.
Wow.
At no point does any decision made inside the active hour ever touch the final hourly close. The future is structurally walled off by the mechanics of the memory array.
Now, conceptually, that makes perfect sense, but from a computer science perspective, there is a major problem with this, right? Doing this continuously in Python is incredibly painfully slow.
Oh, painfully slow. Python is a dynamically typed, interpreted language.
Which means what exactly for a simulation?
It means if you try to run a massive simulation, bar by bar, updating a digital ticker slot and recalculating complex moving averages on every single 1-minute tick over years of historical data using standard Python loops, your backtest might take hours or even days to run.
Who has days to wait for a backtest?
Exactly. Nobody.
But the developer didn't just accept a slow simulation. They built a hyper-fast version specifically designed for rapid testing, right? The source mentions a vectorized, Numba-compiled reimplementation called engine_multif.py. We need to explain exactly how they achieved this speed without breaking that permanent paint rule of the scoreboard.
This is where the engineering gets highly sophisticated. To solve the speed problem, they used a library called Numba.
Numba.
Okay, Numba is a just-in-time, or JIT, compiler. It takes your standard Python code and, at runtime, translates it down into highly optimized machine code.
Wait, so Numba just skips Python entirely?
Basically, yeah. It goes straight to the raw instructions the CPU understands, bypassing all of Python's normal overhead.
Okay, but Numba alone isn't enough, is it? The text specifically highlights that it is vectorized. What does vectorization actually mean when we're manipulating arrays of financial data?
Think about a traditional programming loop. A loop goes to row 1, performs the math, then goes to row 2, performs the math, and so on. It's sequential.
Like reading a book word by word.
Exactly. Vectorization is a way of writing the math so that the processor can perform operations on entire columns of data all at once.
All at once? How?
It utilizes specific hardware instructions in the CPU called SIMD that stands for single instruction, multiple data. But to vectorize a multi-timeframe system without leaking the future, you have to be incredibly careful.
Right, because the moment you apply an operation to a whole column of data simultaneously, you risk accidentally pasting that future 11:00 a.m. close back onto the 10:37 a.m. minute, recreating the naive bug.
Exactly. You could accidentally overwrite the digital ticker with the permanent paint of the future. So the developer engineered a brilliant workaround.
What did they do?
The engine pre-computes exactly how many 1-hour candles have fully closed at any given 1-minute interval. They create a dedicated integer array called n_closed I.
Okay, and closed.
So at 10.37, n closed might explicitly say, hey, 10 candles are permanently closed. The vectorized math is strictly instructed to only calculate the historical moving average using those 10 permanently closed candles.
Oh, I see.
And then it explicitly pins that single known 10.37 running close into the final slot of the array before calculating the current value of the indicator.
So the mathematics are strictly bound by that n-closed index. It means the mathematical contract they've built is unforgiving.
Very unforgiving.
The value calculated at any given minute, which we can call bar I, depends only on the base closing prices from time 0 up to time I. It's like building a watertight vault, where the code physically lacks the variables to even reference time I plus 1. It simply cannot look into the next box.
That is the perfect way to frame it. The engine is constrained by its own architecture. And if we zoom out for a second, think about how profoundly difficult this concept is for human beings to grasp in our own lives.
Oh, yeah.
Think about how often we evaluate our own past decisions using information we only gained after the fact.
We do it constantly. You buy a stock, it crashes the next day, and you beat yourself up saying, ugh, I shouldn't have bought that. It was so obvious the market was overexpended.
But did you know it was going to crash at 10:37 a.m. when you hit the buy button?
No, had no idea.
Right. You only knew it at 11 a.m. when the market rolled over. You're judging your past self using the permanent paint of the future rather than the digital ticker of the present.
That's a great point.
This engine code is the ultimate mathematical enforcement of the rule. You only know what you knew at the time. It forces the machine to live purely, strictly in the present moment, totally ignorant of what is about to happen.
Okay, so the engine is built, the watertight vault is constructed, but any good software engineer knows you don't just build the vault and assume it works, right? You have to try and break into it to prove it's secure.
Absolutely.
The vectorized engine must be tested against the live simulation buffer. And this brings us to the validation phase. Normally, programmers rely on what are called parity tests.
Yes, parity testing is the standard first line of defense in software validation.
How does that work?
The core concept is straightforward. You have your original, slow, perfectly accurate live trading simulator, right?
Mm-hmm.
The running candle buffer that updates bar by bar.
Right.
And you have your newly engineered, lightning-fast, Numba-compiled vectorized engine. You feed them both the exact same mountain of historical data, and you check to see if they output the exact same results.
Sounds logical.
If the fast engine produces the same numbers as the slow engine, you assume they are mathematically equivalent.
And the data set they used to run this parity test is staggering. They used 86,400 bars of real ETHSDT 1-minute data.
Which is Ethereum traded against the US dollar at Tether.
Right. And this data covers January and February of 2024. That is an absolute mountain of raw market chaos.
It is a massive, highly volatile slice of reality. 86,400 minutes of crypto trading contains an incredible amount of chop, momentum spikes, trend reversals, and just pure noise.
Yeah.
And they run two entirely independent checks against two independent references to ensure the parity is absolute.
What's the first check?
First, they check the indicators and the crosses. They replay the live running candle buffer class sequentially, bar by bar, overall 86,400 bars. And they compare every single mathematical event against the fast engine.
When we talk about events, we're talking about those HMA crosses we discussed earlier, right?
Yeah.
The moments where the fast trend crosses the slow trend.
Exactly. And the numbers are substantial. The test evaluates 408 distinct cross events on the 1-hour time frame, 2,792 crosses on the 15-minute time frame, and 3,691 crosses on the ultra-fast 1-minute time frame.
Now, when developers say they compare these events to ensure parity, they don't mean they plot them on a chart and see if they look kind of similar visually. Right.
Yeah, visual inspection is entirely useless in quantitative finance. They check the underlying arrays programmatically. Not one single cross event among those thousands differs in the bar it occurred on, or the direction of the cross.
That's impressive.
But it goes deeper. The actual underlying moving average values match down to a floating point tolerance of roughly 1 times 10 to the negative 15.
1 times 10 to the negative 15. Okay, that is 0.14 zeros and 1. Why isn't it just perfectly identical? Why is there any tolerance at all?
This comes down to a fundamental quirk of computer science called IE754 floating point arithmetic.
Okay, you're going to have to translate that for me.
Sure, computers represent decimal numbers in binary. Because of this, certain decimal numbers can't be represented perfectly.
Ah, like trying to write out 1/3 as a decimal.
Exactly. When you add up thousands of numbers in a slightly different order, which happens when you compare a sequential loop to a vectorized array operation, the tiny rounding errors accumulate. The difference appears way out at the 15th decimal place.
I see.
So a tolerance of 1e15 basically means they are as mathematically identical as the physical hardware of a CPU allows them to be.
Okay, so that covers the underlying indicators. But the source text outlines a second check for parity. What is the second check?
The second check moves from the indicators to the actual business logic of trading. They compare the fast engine's trade logs against a pure Python simulation of the trading rules.
So they actually run simulated trades.
Right. They found exactly 466 executed trades in what they call their dual configuration and 211 trades in their triple configuration.
Did they match?
Field by field, the trade logs are compared. The exact entry bar, the exact exit bar, the exact execution price, the total profit and loss. And the P&L matches to 1 times 10 to the negative 12. 1/trillionth of a unit.
1/trillionth. And the developer didn't just test the happy, easy paths either, did they? The source explicitly mentions they intentionally introduced awkward corner cases into the parameters to try and break the engine.
Yes, this is a hallmark of rigorous testing. They deliberately set an exit threshold higher than the entry threshold.
Why'd you do that?
In a normal strategy, you wouldn't. But by forcing the parameters into an illogical state, they forced the code to execute rare, weird branches of logic just to see if the fast engine would stumble or misalign the timeframes. But it didn't.
It held up perfectly, field by field, identically.
Flawlessly.
But hold on, we have to pause here. Because if I'm a quantitative developer and I run a test on 86,400 bars of volatile crypto data, and the indicator arrays match down to the 15th decimal place, and hundreds of complex multi-time frame trades match down to a trillionth of a unit of profit, I am popping champagne.
Naturally.
I'm calling my investors. Aren't we done? We've proven the fast engine perfectly replicates the live engine.
See, this is the exact cognitive trap that destroys so many quantitative funds. Parity testing is necessary, but it is wholly insufficient for proving a system is fundamentally sound.
Let me use an analogy here to see if I am grasping the flaw in parity. If I have two digital clocks on my wall and they both say exactly 12.0000 down to the millisecond, they are perfectly in sync. I have proved they match. But I haven't actually proven that either of them is telling the correct time, have I?
Exactly. Your analogy hits the core epistemological problem of parity testing.
Okay.
Parity only proves that your fast backtesting engine perfectly matches your slow reference engine. It proves they are identical.
Yep.
But what if the reference engine itself, the slow simulator you assume is correct, has a hidden look-ahead bug?
Oh, what?
What if the LiveBot simulator was built wrong in the first place? If your foundation is cracked, all parity proves is that you have faithfully, brilliantly, and perfectly reproduced a time machine.
Wow. So agreement between the two software systems just tells you they are mathematically symmetrical. It tells you absolutely nothing about whether they are actually obeying the laws of time and causality.
It tells you nothing about causality.
Yeah.
Returning to your clocks, two clocks perfectly in sync doesn't mean one clock causes the other to tick.
Right.
And it certainly doesn't prove that they aren't both synced to a time that is 5 hours fast. If your reference system is leaking the 1 hour close into the 10:37 a.m. decision, and your vectorized engine perfectly copies that leak, you will pass a parity test with flying colors.
And you'll think you have a working system.
And you will still lose all your money in live trading. To prove that your system is not secretly looking into the future, to prove true causality, you need a completely different paradigm of testing.
So, driven by this realization that parity is just an illusion of safety, the conversation in the source text pivots to the ultimate proof, the holy grail of temporal validation.
If you want to definitively test for causality, you have to do the one thing you can't do in the real world. You have to change the past. Welcome to the Shifted Future Probe.
This is where the computer science transforms into something almost philosophical.
How so?
Well, the developer realized that the definition of a look-ahead bias is strictly operational. Look-ahead literally means a decision made in the past depends structurally on data that only exists in the future.
Okay.
So the logical contrapositive of that statement is this. If you artificially change the future and a past decision moves, alters, or recalculates in any way whatsoever, then this past decision was secretly reading the future.
We have to try and break the timeline. If we want to see if A causes B, we can't just look at them. We have to violently alter A and see if B flinches.
It is a literal time travel test. You reach into the data set, you rewrite the future brutally, and you meticulously audit the past to see if the ink on the historical ledger magically changes color. Let's break down the exact physics of how they execute this brutal time travel test in the code, because it's fascinating. The author picks a specific moment in time, a coordinate they call a cut point, denoted as J.
Right.
They place this cut point at exactly 60% of the way through the historical data series. Out of the 86,400 bars, that is bar number 51,840.
That cut point acts as an impenetrable temporal wall. Everything strictly before bar 51,840 is designated as the past.
Yeah.
Everything from bar 51,840 onward is designated as the future.
Okay, we have our wall. Now what?
And then the developer does something incredibly disruptive. They perturb every single data point in that future.
How?
They take every single closing price and opening price from that 60% mark all the way to the end of the data set, and they multiply it by 1.05.
They give the entire market a 5% shove upward. I mean, in financial terms, an instant sustained 5% gap up across tens of thousands of consecutive minutes is a massive cataclysmic market event.
Oh, it's totally unnatural.
It would completely alter every moving average, every trend line, every momentum indicator.
It completely rewrites the reality of the data set. So now the future is drastically, violently different than it was in the original parity test.
Right.
The developer takes this newly mutated data set and runs the entire multi-timeframe vectorized engine again. They recalculate the 180 reads per hour across all 86,400 bars, and then comes the ultimate assertion.
What's the assertion?
They assert programmatically that everything strictly before that cut point J must be bitwise identical to the original unperturbed run.
And when the author says bitwise identical, they are applying the strictest possible standard in computer science, right? They use a NumPy function called np.array_equal. We need to explain why this function is so ruthless compared to standard mathematical checks.
Yeah, when you use standard mathematical checking, you might allow for floating point errors, or you might just check if the final output of the trade matches. np.array_equal checks the raw memory of the arrays.
It looks at the actual bits.
Exactly. It verifies that every single moving average float value, every single Boolean cross flag, every single separation distance metric on those 51,840 pass bars is the exact same sequence of bits.
Wow.
Furthermore, time series data often contains missing values, represented as nans, or not a number. In standard Python, if you ask if nan equals nan, the program returns false. It is a known quirk.
Wait, really? Nan doesn't equal nan.
Right, it's a weird quirk.
Yeah.
But np.array_equal is specifically instructed to verify that even the missing data, the nans, perfectly align in the exact same memory slots.
So it is a relentless audit. What was the result of this massive temporal audit?
The engine passed, unequivocally, for all three timeframes, the 1 minute, 15-minute, 1 hour clocks,
Yeah.
and for both the dual and triple trade simulations.
Nothing changed?
Nothing. Perturbing 34,560 future bars left the 51,840 pass bars completely untouched. Every trade that opened and closed in the past, every mathematical calculation remained exactly as it was. The ink on the historical ledger did not change.
To bring this back to a physical analogy for you listening, imagine a master ledger of financial records. If someone audits that ledger, and the auditor discovers that when you write today's entry on page 100, the ink on last year's entries on page 50 magically changes its value, the entire ledger is structurally compromised.
The database is corrupt.
Exactly. By proving that a massive edit to page 100 leaves page 50 perfectly intact, the algorithm proves its timeline is secure. The past is structurally walled off from the future.
What makes the shifted future probe particularly brilliant is that it is completely time-frame agnostic.
What do you mean by that?
The logic of the test doesn't care about the 15-minute clocks or the 1 hour clocks. It doesn't even know they exist in the strategy logic. It simply looks at the raw stream of base data arrays.
And why is that structural blindness important?
Because it makes the test universal. If that naive resampling bug we discussed at the beginning actually existed in the code where the 1 minute bar accidentally peaks at the final 1 hour close, this test would catch it instantly without needing to know how the bug works.
Oh, I see.
Imagine the algorithm is processing a minute, that is 1,000 bars before the cut point J. But those 1,000 bars are technically inside an hour block that eventually crosses the cut point.
Right.
If the algorithm was secretly waiting for that hour to finish to get its data, the 5% shove at point J would artificially inflate the final closing price of that entire hour. Suddenly, the indicator 1,000 bars in the past would change because it was secretly reading a final close that just got bumped by 5%.
And the test would catch that.
The np.array_equal assertion would immediately fail. The probe would light up and halt the program.
Okay, the elegance of that is undeniable. It uses the physics of the array against itself. But I have to push back here, because anytime a test yields a perfect result, my inherent skepticism flares up.
Fair enough.
What if the test itself is broken?
Elaborate on that. How could the test be broken?
Well, what if the 5% shove just didn't register? What if the code processing the perturbation is flawed and it just ignored the 1.05 multiplier entirely? If the future didn't actually change in the machine's memory, then obviously the past wouldn't change either. If a test always gives you a green check mark on a process that was completely dead to begin with, aren't we just manufacturing false confidence?
That is a phenomenal observation, and it is the exact mark of a truly paranoid, elite, quantitative developer to ask it.
Well, thank you.
A test that cannot fail proves absolutely nothing. If multiplying the future by 1.05 somehow changed nothing anywhere in the output arrays, then stating the past is unchanged is a trivial, logically meaningless statement. The probe cannot just be a passive wall. It needs aggressive teeth.
So how does the developer give the probe teeth? How do they test the test?
They enforce the validity of the probe with two additional absolute assertions. Assertion 1 guarantees that the future must actually change.
Okay.
The code specifically asserts that the 5% perturbation did, in fact, mathematically alter the cross events somewhere after the cut point J. It checks the Boolean arrays and verifies that the flags are different.
So it proves the shove actually worked.
Exactly. This proves the engine is actively processing the mutated data. It proves that the future was genuinely rewritten. The chaos propagated forward through the arrays, but crucially, it did not bleed backward across the boundary.
So the chaos was real, but it was successfully contained. What is assertion 2?
Assertion 2 is even more precise. It proves that the boundary of the temporal wall is exact. Not 1 minute early, not 1 minute late.
How do they test that?
To achieve this, they abandon the massive 5% future shove and run a hyper-localized test. They target a single bar, just bar j, and only bar j, and perturb it by multiplying the close by 1.02.
A 2% nudge on one isolated minute.
Yes. Then they assert two things simultaneously. First, the entire pass prior to j is mathematically untouched. Second, the indicator precisely at bar j reacts instantly to the 2% nudge.
But wait, if you shove a single minute, how do you know the engine isn't just reacting a minute late? Wouldn't you need to verify that there is zero lag?
That is exactly what the single bar test proves. It is the absolute knife edge of closed bar semantics. If the indicator reacted at bar j plus 1 instead of bar j, the system would have a built-in lag.
Which is bad, right?
In live trading, a 1-minute lag means you execute your trade after the momentum has already passed. It destroys profitability. Conversely, if it reacted at j minus 1, it would have a look-ahead leak.
Right.
By programmatically asserting that it reacts immediately on the exact perturbed bar and not a millisecond before or after, the developer proves that there is zero mechanical delay and zero temporal foresight.
Okay, so let's tally up the sheer volume of validation going on here. We have 9 distinct mathematical checks on indicators and moving average crosses across 3 different time frames.
Right.
We have 8 checks on the trades themselves, validating entry points, exit points, and P&L between dual and triple configurations. And we have 8 shifted future probe checks, proving causality, localization, and verifying that the probe itself actually has teeth.
It's exhaustive.
That is 25 rigorous mathematical layers standing between this engine and a fabricated backtest.
25 checks. And we have to ask the ultimate question, why go through all this trouble? Why write hundreds of lines of complex testing code just to prove your moving averages are aligned?
Why do it?
Because earlier in the author's series of articles, they noted a terrifying reality about quantitative finance. A simple look-ahead leak, just a tiny, almost imperceptible peak at a forming 1-hour candle, can fabricate a Sharpe ratio of 15 out of pure mathematical noise.
We need to define the Sharpe ratio for context, because a Sharpe of 15 is difficult to comprehend if you aren't staring at backtests all day.
Go for it.
The Sharpe ratio is a measure of risk-adjusted return. It basically asks, how much return are you getting for every unit of volatility you are enduring? In the real financial world, a Sharpe ratio of 1 is considered decent. A Sharpe of 2 or 3 is phenomenally good. It's the kind of performance that gets you billions of dollars in institutional capital. A Sharpe of 15 is not just good. It is an ATM that spits out $100 bills, never asks for your PN, and never suffers a drawdown. It is physically impossible in real chaotic markets.
It is a complete mirage. And here's why it is so dangerous. When developers build strategies, they don't just guess the parameters. They run an optimization search.
Right.
They give a computer a grid of parameters. For example, test every HMA period from 10 to 100 and every exit threshold from 1 to 5. The computer runs tens of thousands of backtests.
Just grinding through every combination.
Exactly. If there is a look-ahead bug hidden in the multi-timeframe logic, it might only manifest when a very specific exit threshold aligns perfectly with a higher timeframe close. The optimization algorithm, whether it's a grid search or a genetic algorithm, is utterly ruthless and completely blind.
Doesn't care if it's real.
It doesn't know what is real alpha and what is a software bug. It will hunt down any leak, exploit it to the absolute maximum, and blindly hand you a fake winner with a Sharpe of 15 because that parameter set mathematically produced the highest number.
And if you don't have the shifted future probe, you will look at that Sharpe 15 and think you are a genius. You will wire the algorithm to real capital, deploy it to a live exchange, and you will lose everything.
Every penny.
Because the live bot, operating under the brutal reality of real time, physically cannot peek into the future. The probe is the only mechanism that allows you to trust that the optimization engine found a real edge, rather than just exploiting a time travel bug.
Exactly. The optimization engine is like an evolutionary process that selects for the most profitable trait. If time travel is a physical possibility in your code, the algorithm will evolve into a time traveler.
That is such a good way to put it.
The probe ensures the physics of your simulation map precisely to the physics of reality.
Okay, so a listener hearing all this, 25 flawless checks, mathematically proven causality, watertight memory vaults, vectorized engine speed. They might be thinking, wow, this developer has solved the market. This algorithm is flawless. This is a guaranteed money printer. We need to ground ourselves back in reality. What does this massive validation framework not prove? What are the limits of this evidence?
That is the most crucial, humbling part of this entire analysis. The shifted future probe proves one specific narrow thing. On this exact data set, no mathematical decision before bar J depends on data after bar J. The information boundary in time holds perfectly. That is it.
So it doesn't actually prove the strategy is any good.
Not at all. It does not prove the strategy has a genuine market edge.
Huh.
A perfectly causal, perfectly sealed, completely bug-free engine can still lose money, honestly.
Honestly, losing money.
In fact, most of them do. The probe is entirely silent on the economic reality of profitability, proving you aren't structurally leaking the future, and finding a genuine mathematical edge that outsmarts the market are two entirely separate, massive jobs. Conflating them is exactly how technically sound, mathematically perfect, but strategically terrible backtests get deployed and lose millions.
And what about biases that have nothing to do with time, like survivorship bias?
Exactly. The probe does not cover non-temporal biases. It doesn't know if you only tested your algorithm on cryptocurrency coins that happen to survive the 2022 bear market. That is survivorship bias.
Right, ignoring all the coins that went to zero.
Yes. It doesn't know if you cherry-picked this exact Jan-Feb 2024 dataset because you looked at a chart beforehand and knew it visually matched your strategy. That is selection bias.
Oh, that's a big one.
It doesn't know if your fee model is way too generous and ignores the very real spread and commission fees that exchanges charge on every single trade.
And what about the actual physical infrastructure of trading? The speed of light, internet cables, exchange routing?
The probe operates strictly on the internal decision path of the algorithm's logic. It does not prove that your live execution fills will match your backtest fills. In the real world, the market is a physical place. Slippage exists. Latency exists.
You don't always get the price you want.
Your bot calculates the HMA cross, decides to buy, and sends an order over the internet. In the 50 milliseconds it takes for that packet of data to reach the Binance or Nasdaq Q servers, high-frequency trading firms may have already moved the price against you.
Yeah.
Your backtest assumes you get the price you saw. Live trading guarantees you often won't. The shifted future probe is completely blind to that gap.
The author also admits one technical caveat about the physics of the probe itself. The tests they documented only cuts the dataset at a single point, at 60% of the series. If a developer wanted to be truly, deeply, pathologically paranoid, wouldn't they need to sweep that test point across every single minute?
Yes. A highly paranoid version of this probe wouldn't just test bar 51,840. It would iterate. It would set J to bar 2, run the massive simulation, set J to bar 3, run the simulation. It would sweep J across every single one of the 86,400 bars.
But the computational cost of that?
Astronomical. And frankly, the author considers one well-chosen cut at 60%, combined with that highly localized single-bar check, to be mathematically sufficient.
Why is that sufficient?
Because a temporal leak that somehow completely hides from a massive 34,000-bar future perturbation at the 60% mark, but magically appears at the 40% mark, would have to be an incredibly strange, highly complex bug.
It would have to be almost sentient to hide from the probe like that.
Exactly.
But it really comes down to a philosophical point about evidence, doesn't it?
It does. The point of building a 25-step validation framework is to intimately know the absolute limits of your evidence. It is not to pretend that a single test, no matter how mathematically rigorous or elegant, is a universal quantifier that solves all the chaotic realities of the financial markets.
Right.
But to the developer's massive credit, the structural gap between the backtest simulation and the live trading bot is essentially closed by construction. Because the Numba-compiled backtest engine and the Python live bot both share the exact same running candle buffer core architecture. The temporal rule proven by the probe is the exact same temporal rule executed in live trading. The permanent paint and the digital ticker behave identically in both environments.
So, to summarize the massive technical architecture we've unpacked for you listening, if you are building, evaluating, or investing in multi-time frame quantitative strategies, you must remember that they leak through the forming bar.
Really do.
They leak through the subtle difference between the running close and the final close. The leak is almost never in the execution fill, is deeply embedded in the mathematical indicator itself. And if you really want to prove causality, if you want to prove your machine isn't a time traveler, you cannot rely on parity.
No, parity's an illusion.
You have to forcefully perturb the future, assert the past remains unchanged, and ensure the test itself has teeth.
If the past doesn't flinch when the future is rewritten, you are truly trading in the present.
This exploration into data validation is fascinating on a technical level. But as we wrap up, I can't help but think how this concept of look-ahead bias extends so far beyond just quantitative algorithms and Python arrays.
It really does.
Yeah.
The shifted future probe raises a fascinating, deeply provocative thought about human psychology.
Yeah.
If a highly scrutinized algorithmic backtest, written by a professional developer, can so easily leak the future, if a machine can falsely generate a sharp ratio of 15 just by accidentally peeking at a forming 1-hour candle, how often are human beings doing the exact same thing subconsciously in our daily lives?
Think about financial analysts on television, or macroeconomic forecasters, or even sports pundits breaking down a game on Monday morning.
Exactly. When we analyze past market crashes, or historical geopolitical events, or a coach's controversial play call in the fourth quarter of a championship game, how often are we genuinely evaluating their decisions based purely on the running close of the limited, chaotic information they actually possessed at that exact minute?
Wow.
And how often are we secretly, unfairly judging them using the final close of the perfect hindsight we possess today? It is incredibly difficult, maybe impossible, for the human mind to unknow the future once the future has happened. We leak the future into our judgment of the past every single day.
We sit down to take the history test of life, but we constantly leave tomorrow's newspaper on our own desks. We judge past decisions as if the outcome was always guaranteed.
Precisely. If a lifeless machine requires 25 relentless mathematical checks to prove it isn't cheating the flow of time, maybe we should be a little more rigorous with our own hindsight. Maybe we should recognize when we are leaking the future into our judgment of others.
That is a phenomenal, humbling thought to leave on. Thank you so much for joining us on this custom-tailored deep dive into algorithmic validation. We hope it gave you a new lens, not just on quantitative trading or computer science, but on how we validate the flow of time, causality, and information itself. Keep questioning your data, stay deeply curious, and we will catch you on the next deep dive.